not going to get to see anybody's. I'm not going to get to see anybody's faces. I was just going to be talking into the blank. So I'm kind of going to be hoping that you're there, hoping that you're that you can hear what is not quite the same as being in the room, but it does allow us to have bigger audiences because we we can take the travel out of things. So without further ado, I'm going to jump into my talk. I hope you can all hear me okay. So, am I coming through? Good. I've seen the thumbs up. That's all I need. So without further ado, I shall jump into my talk. And my next question is to say, can you all see my screen okay?
Yes.
Yeah.
Yeah. Before I So very good. So as Nick said, I work in automotive propulsion research. That's anything to do with what makes vehicles go at the University of Bath. And what this talk is going to be about is pretty much an overview of automotive propulsion research at the University of Bath. I know you've seen Nick gave a really good introduction to me, but I always think it's nice to just tell you a little bit more about my backstory before jumping into this. So I grew up near Paris, and there's a very young me in the top right-hand corner. I think up Notre Dame Cathedral. And in 2003, I joined the University of Bath as a student, and that's me revising for my final exams for my undergraduate degree. A few years later, I received a PhD from the University of Bath, and that's young graduate me in 2011. And that was for research on cooling systems of diesel engines, so diesel thermal management, the kind of thing you'll find in transit vans. In 2012, I became a member of the faculty and what we might call an independent researcher. And since then, I've had the privilege of working on a whole range of technologies associated with the movement of vehicles, starting with turbocharging, but also including hybridization. So that's the use of electrical energy alongside traditional combustion engines. From there, I've been able to work on electric machines, so electric motors. So making, I would say, that transition from the combustion engine to electric machines, maybe 10, 15 years earlier than we expect to do it within the passenger vehicles available on the road. And I've also done a lot of work around kind of measurement techniques and that are associated with vehicles. And then earlier this year, I became a professor within the university, and so now a big chunk of my role is spent like this, working with students, with younger researchers, nurturing them to work on these kind of research projects. I'm based in Bath, and for those of you who don't know where Bath is, it's a relatively small city in the west of England, just shy of about 100,000 people who live there, and about 20,000 students. So a very, very large student population, very, very famous for the Roman baths, Georgian architecture, Jane Austen, and rugby, although there hasn't been too much success in Bath in the time that I've been there. The university, which is where I work, although I haven't spent that much time up there in the last 15 months, is situated about 2 miles out of the city centre on the top of a hill. It was built in the 1960s, it was founded in 1966. And it's primarily a technical and engineering university. So most of the staff, students in the university are based around mechanical, civil, electrical engineering, physics, chemistry, biology.
Yep.
We are very regularly one of the top 10 universities in the country. And so within the university, I work in the Department of Mechanical Engineering, which has about 250 students graduating each year and about 100 PhD students. And within mechanical engineering, so I obviously work within the automotive group, but we also have an aerospace group, manufacturing, hydraulics, motion control, sustainability, costing, engineering management groups that all interact with each other within that department. So hopefully that just gives you a little bit of context to my speak about who I am and where I work before I now start to really focus on automotive research. So I'm going to go through three main aspects. I'm going to talk about our origins and who we are as an automotive research group first of all. Then I'm going to move into giving you some insights into our recent work kind of over the last 10 years on combustion engines, electric machines, batteries, and emissions reduction. And then I'm going to finish by talking a bit about our future and explain to you what that really long acronym IAAPS was that Nick introduced me with. So let's move on to our origins. So the university was founded in 1966, and so was automotive research at Bath. So it was well before I was born. But the origins of our research are really in looking into two-stroke diesel engines and turbocharging two-stroke diesel engines. And I was lucky enough to join the automotive research group in time to meet the founding professor of automotive research at Bath, Professor Frank Wallace. At the time, he was about 95 years old, and he was still coming in and sitting down and working out fundamental equations of fluid mechanics inside turbochargers in the same office as I was as a young, enthusiastic PhD student who was getting a computer to do all that for me. It was really real privilege to be able to meet him. But sort of moving on towards our more recent time, which is what I'm going to focus on here. This is a sort of timeline of some of the key growth and changes in activity that we've had. So in 2005, we started out in what we call lean powertrain development processes, and this was really the start of us as a group doing something really a bit different and relying on computer simulations combined with experiments in order to be able to develop engines and transmission systems. At the time, it was very much focused on the technologies of the time. But moving forward, in 2009 was the first time that we started working on both hybrid vehicles. So looking at the time, it was a retrofit hybrid system that a small company down in Exeter called Ashwoods were making. So they took transit vans and they would retrofit a small hybrid system to improve fuel efficiency. And it was also around that time that we started working on extreme downsizing, and I'll talk a little bit more about this engine called Ultra Boost a little bit later in the talk. Early in the 2010s, we branched out and started working on driver behavior and how we could develop systems that allowed for a better interface between the machine, so the engine and the car, and the driver, in order to promote fuel efficiency. And again, I've got a bit more on this later on. This is a system called Lightfoot, which is a sort of driver coaching system that sits within the vehicle. As we moved on in 2013, we got our first project actually developing electric motor technologies. And this was a really strategic decision on our behalf to move away from just combustion engines into the field of electrification. And so to begin with, in 2013, we were working on the mechanical design of electric motors. And in 2017, we were lucky enough to start working on actual motor control. So really breaking down those boundaries between mechanical and electrical engineering. On the way in 2014, we started working with a small company in Bristol called HIETA, who specialize in additive manufacturing. And we were developing things like really compact heat exchangers, or in this case, cooled turbine wheels with sort of internal geometries that you can only make through 3D printing, but 3D printed using metal. So they're actually useful parts that you can put inside a real mechanical system. And then moving on to sort of our most recent activities. So in 2020, we launched our first project around hydrogen fuel cells for heavy duty vehicles. With Cummins Turbo Technologies. So that's a project that's currently occupying most of my time. And just earlier this year, we published our first publication on battery systems, and again I've got a few insights on that for you a little bit later on. So that's kind of what we do. Now, who do we do it with? Well, pretty much everything that we do is in collaboration with industry, both in the UK and overseas. And here are just some of the names of the people who we work with and who sponsor us and who we collaborate with. So hopefully you'll recognise some of these names as that I've mentioned already. They'll mean something to you. And because of our strength in terms of our collaboration with industry, in 2015, we were appointed a spoke of what's called the Advanced Propulsion Centre network. So the Advanced Propulsion Centre is an organisation that was set up by the automotive industry and the UK government in collaboration with each other to support UK manufacturing and UK research and development. And we're one of 6 spokes with a specialism around system efficiency at the university. We're there to coordinate research and development between different organisations, different aspects of the automotive sector. We're really a group that has grown enormously over the last decade, and on the left hand side are just some of the graphs in terms of what we do. These are not COVID cases. These are numbers of published papers. These are the amount of grant income that we have that we've received, and the number of PhD students that we've had starting within our group. So really a real strong growth over the last 10 years. And on the right hand side here, you can get a picture of kind of who we are working with. So we work with what are called original equipment manufacturers. So they're people who make cars, make vehicles, make engines. So Ford, JLR is the two fund about half of our research. But we also work with tier 1 suppliers. So I talked about Cummins Turbo Technologies. They're a big supporter of our work, as well as Shell and BP as kind of fuels and energy providers. And then also we do, probably about a fifth of our work with small and medium enterprises. So working and seeing them grow from real startups to really established companies is a really satisfying thing to be involved with. This is, I always like to bring it back to the people, because you can put pictures and logos and nice facilities and stuff, but actually what goes on and the reason that this works is because of the people involved. And we are humans behind the scenes. We can be called researchers, professors, PhD students, whatever, but at the end of the day, we are a group of humans who are really passionate about what we do. And this is just a couple of snapshots that I pulled out from 2012 and then from 2016, and you can see the growth of the group over that period of time. It is also about what we can do, though. And these, just so I give you some pictures of the kind of working environment that we have within the university. So at the moment, these are facilities that exist in Claverton Downs, on the outskirts of Bath, in terms of facilities to be able to test engines. So these facilities are setups where we have an engine, so just really taken out of the bonnet from a vehicle, and we directly connect that up to a series of electric motors. And these electric motors are then linked to a computer, which controls them in a way that simulates the rest of the vehicle. So then we can run this engine as if it was in a vehicle, but without actually having the vehicle present. And it means we don't have to go out on the road. It means we can put all of these cables and wires, which are there measuring things like temperatures and emissions and so on, and are far too heavy to carry around on the road. And we can do sort of high precision, repeatable investigations looking at things like efficiencies and the effectiveness of new technologies. So we have a few facilities that look like this for engines. We have a facility for testing whole vehicles as well, called a chassis dynamometer. And so here we can bring a vehicle into a climatic chamber, where we can control the temperature between -10 and +50 degrees. And then the car sits on some 48-inch rollers that are located under the ground. And as you drive the car, the rollers are rolling, so it's a rolling road. And they're connected again to an electric motor that applies a resistance to simulate driving along, aerodynamic forces, driving up hills. And what this enables us to do is, again, have all that instrumentation suite to install something like this, a robot driver, so we can have very, very repeatable test cycles. So we can look at new technologies and their effectiveness in terms of efficiency and emissions. And then we have sort of more specialist labs like this. So over on the left-hand side, this is something for testing a transmission. So where we have one electric motor driving another electric motor. So one simulates an engine, one simulates the vehicle, and we can test any kind of transmission or torque converter in the middle. Or over on the right-hand side here, which this sort of mess of pipeworks is a contraption designed to test turbochargers. So right in the middle here is a turbocharger, which is our test piece in this particular case, and all the bits around it are there to try and replicate what would happen on the engine, but in a very repeatable and controlled way. And so with all those people, all those facilities, I just wanted to summarize a little bit where we fit in and what we're trying to do as when we work with Ford and Jaguar Land Rover, what are the things that we're trying to do? And I'm going to start just by explaining a little bit about how vehicle development has typically worked in the past. So typically, at the very, I'm going to plot out a few activities that people within those companies would be doing over time. And on the bottom axis of this graph here, I'm going to represent cost or complexity of doing something. So over on the left-hand side, it's very simple, it doesn't cost very much. And over on the right-hand side, it's quite complicated and very expensive. And on this y-axis here, I'm going to talk about realism. So how real, how close to the real thing is the activity that we're doing. And so typically at the beginning, when a company decide they want to develop a new engine or a new car, they will start by doing some simulations, so some models. So they'll get a computer, some computer software, they'll build up a model of an engine, and they'll run those simulations. And that's relatively inexpensive. All you need is a computer and a software license, but it's not particularly real because it's all just mathematical equations, assumptions that simplify the real world. And once you are happy with that step, you will gradually progress to more and more closer to realism. So these are some of the facilities that we saw before. So a very basic engine test on a dynamometer, like I showed you before. So a real engine, but a modeled vehicle. And at the next level, we might actually have a vehicle on a rolling road. So here we have a real vehicle, but it's not actually outside. And then at the top, we have a real car driving around a real road. And this gets progressively more and more real, but it also gets progressively more and more expensive because you have to engineer more and more of the car. And what happens is at different points along that way, you might try to improve this kind of modeling and simulation work to make it more real. But you can only do that if you've actually gone and built this particular test car. And so if you get to the point of building this test vehicle and driving on the road and you realize that you've done something wrong, then it's actually really, really expensive to go back around the loop and re-engineer something, because you've got to undo a lot of the work that you have already you've already done in order to then go back along those green arrows. So this is a sort of status quo of the development process. And what we are seeking to do is to take things like these basic tests and these simulations and do research to improve those models, improve those experimental techniques to try and improve the realism of these lower cost aspects of vehicle development. And if we can improve the realism of these low cost elements, then it means we're more likely to get things right as we advance into the full vehicle and on-road tests. And what that does is it minimizes the chance that we will have to do these very expensive iterations or development loops. So that hopefully gives you sort of now an overview of what we are, who we work with, and what we do. And now I'm just going to jump into some of our recent research activities. So these are now some examples of the things that we that we do. As said before, we kind of work on all aspects of the propulsion system. We started out as an engine group, but we've also expanded to turbocharging, electric drives, and so on. I'm just going to cover a few of these aspects as I go through the talk. I'm going to start by just giving an example from research on combustion engines, which is really where we started as a group. And if we take a typical engine, engines operate over a certain speed range, so you'll be quite familiar with that from looking at the rev counter between 1,000, 4,000 RPM for a diesel engine. But at any of those speeds, they can generate a certain amount of torque or a certain amount of force, which is roughly equivalent to acceleration that you would feel from the vehicle. And depending on how much torque and what speed your engine is running at, you get a different level of efficiency. And it turns out engines are most efficient when they work at quite high loads and relatively low speed. So this green area here, this is an efficiency map, and this green area is where you get high efficiency. But that doesn't really line up very well with where we tend to drive when we're doing normal driving. So when we're just normally driving around, we spend most of our time down in this bottom left-hand corner, which is quite a low efficiency area for the engine. So what we want to do is to try and develop engines where we move that efficiency area down to where we tend to drive. And that's really the premise behind turbocharging engines. You turbocharge engines to make them smaller. So you make a smaller engine more powerful, so it has a higher efficiency at a lower operating torque. And that's really the reason why most cars today are turbocharged. And that's also really the principal benefit that you get from mild hybridizations, this ability to modulate where the engine is. So what we're talking about doing is replacing big engines with small ones. And that's quite an extreme example, but this is moving on to another extreme example, which is a project that we ran with Jaguar Land Rover in 2009 called UltraBoost. And this, the aim of this project was to create a 2-litre 4-cylinder engine that had exactly the same power and torque capabilities as the outgoing 5-litre V8 engine inside the Jaguar Land Rover product. And the carrot, if you like, the reason for doing this is if you could replace that 5-litre engine with this 2-litre 4-cylinder engine, then you're talking about a 35% gain in efficiency. So 35% less fuel consumption from that change in engine, from delivering while still delivering the same power, the same torque characteristics. So that sounds great if you can deliver that, but it's not that easy, and it's not that easy because once you start to shrink the engine down, you start to ask more and more of that engine. So you ask it to work at much higher pressures, and you ask it to work at much higher temperatures. And here you can see the temperature of the exhaust gases coming out of this experimental engine are really making all of the exhaust pipe glow red hot, really sort of all the way to where we get here in this kind of first sort of cooling stack where we've got some airflow flowing over it. So you can really get pretty hot conditions with this. And when you do that, when you make an engine work a lot harder, you run into a challenge of something called knocking. So to explain what knocking is, I just need to talk a little bit about how combustion happens inside an engine. So inside a petrol engine, if you've ever owned one, you'll know that they have something called a spark plug in them. And the spark plug is as it says, it's a plug that develops a spark, and that spark is designed to ignite the mixture of fuel and air inside the engine at the time that we want it to ignite, such that you get a combustion that is efficient, that is timed at the right time with respect to the motion of the piston of the engine. And that's what so ideally what we want is a combustion chamber filled with fuel, and we spark the spark plug, and we get the controlled combustion of what's going on. But if we downsize an engine, make it a lot hotter, what can happen is we can start to get hot spots that build up somewhere around the combustion chamber. So what can happen is before we ignite the fuel with our spark, a hot spot maybe somewhere on the other side of the engine can ignite the fuel. So without there being a spark, we get this ignition, this auto ignition, or what we would refer to as a pre-ignition. So the fuel ignites before we want it to ignite. As that's combusting, we actually deploy a spark, and we start combusting the fuel from the spark plug. And what then happens is we start to have these two combustion flame fronts which are moving across the chamber, and then they collide in the middle of the combustion chamber. And when those flame fronts collide, we get some really big oscillations in terms of the pressure inside the cylinder. We can generate some really dangerously high pressures inside the engine. And so to give you an example of what that looks like, these are just some measurements of pressure during the combustion event inside an engine. So we have during a compression cycle, we have a rise in pressure, and the fuel would be ignited about this point. We get a big rise in pressure due to fuel ignition. And you can see this black curve here where we've got this oscillation of pressure. That is pre-ignition occurring that is causing these big oscillations in pressure. And if you let them get out of control, you can completely destroy the engine. You can completely destroy the valves inside the engine, and so you have to be really careful and manage this pre-ignition. And the problem that you run into in terms of pre-ignition is it starts to really limit how you can use an engine and how much you can downsize it. And so what I've got here is some plots for the Ultra Boost engine showing the amount of torque. So essentially, this is how much acceleration we can get from the car. versus what's called spark advance. Spark advance is the angle at which we decide to ignite the fuel during the combustion cycle. And at one end of this, we have what's called our not limited spark advance. So this is a limit that we cannot exceed without that pre-ignition, that dangerous combustion occurring. And as we try to generate more and more torque, so make the engine more and more powerful, we see that this red limit here gradually moves over and over to the left. So it's asking us to have the combustion later and later and later in the engine cycle. But there's another limit, which is to do with how hot the exhaust gases are when they come out of the engine. And you saw the exhaust pipe glowing red hot earlier on in a few pictures ago. And eventually you start to melt the exhaust components if you go too far. So this is another limit. And what you can see is these two lines are converging on a single point up here. And that becomes the limiting factor. You cannot go below that, or you cannot go above that amount of power for this particular type of engine, unless you start to do something a little bit different. And what you can do that's a little bit different is you can start to inject not just air into the engine, but you can start injecting gases that help you reduce the temperature or help you reduce this pre-ignition phenomenon. And some of you may have heard about EGR, so exhaust gas recirculation. If you've ever owned an old diesel, you've probably had an EGR valve that has failed when you've needed to go to the garage. And it turns out if you use this technology, this EGR, in a gasoline engine, it can actually really help for preventing knock. And so this contraption here is essentially a research rig designed to pump exhaust gases around that Ultra Boost engine. And if you do that, it turns out you can actually get two benefits. You've got what's called a thermal effect. So you can actually reduce the temperature of the exhaust gases, which means you can move this green line over to the left. And you have a chemical effect, which means you can move this red line higher. And overall, that means you can go and get more power out of your engine. You can downsize it even further. If you can downsize it even further, you can achieve those 35% fuel economy that I was talking about before. And so our research is all about understanding that phenomena, being able to model that phenomena. And I'm really pleased to say we've been able to apply that knowledge in engines like Ford's 1-litre EcoBoost engine. So the engine that you'll find in pretty much every Ford Focus now. They replaced their 1.6 engine in about 2012. And our research features in some of the elements of that engine that are delivering some quite significant CO2 benefits, as well as what we've done on the Ultra Boost engine that I've described to you. So that's engines. Now I'm going to move on and talk a little bit about electric motors, because electric motors are the new form of traction, and they pose a very, very different problem. Now, I'm not going to talk about motors for quite as long, so we haven't got quite as much history working on electric machines. But I wanted to start just by explaining a little bit about how electric machines work. And this is a funny animation that I found on Google earlier this week, which shows which shows the principle of an electric motor. And the principle is quite simple. We've got a magnet. So you see this north and south here, which is spinning around a set of electrical coils. And the magnet is spinning around. And as we energize these different electric coils with electric energy, they also become a magnet, but a magnet that we can switch on and off. And by switching and rotating where the north-south of these coils are with respect to the permanent magnet that is sitting on the rotor, we can constantly have these coils pulling the rotor around around these coils in kind of the same way that a carrot will pull a donkey along. And that's in very simple terms how an electric motor works. But what this graphic also shows you is that it's not a continuous pull. You only have a finite number of these coils, and you have to switch them, and you have to switch them at the right time. And there's these green arrows which keep appearing, which are showing you kind of the amount of magnetic force which is pulling the rotor around those coils. And at the beginning, just after you've switched, that pull is quite strong. But then as the magnet aligns itself with those coils, that force gradually disappears. And so what we have is this oscillation of the force, or you get a ripple over time. And that is, if you're driving slow enough and with a sufficient amount of load, you can actually really feel that inside a vehicle that is driven by an electric motor, and it starts to manifest itself as a speed ripple. So just over here on the right-hand side, I've got a small graph which shows some experiments that we did with one of these electric motors, where we were trying to spin the motor at 25 revolutions per minute. And the blue line is the speed that we actually measured. So you can see this oscillation between about 20 and 30. And if you're driving along, that's essentially a really jerky ride. That is that is not very comfortable to be in that vehicle. You really notice it. And in electric vehicles, which are sort of renowned for being quiet, for having very low vibrations, this can be a real problem that that we need to overcome. And so some of the research that we did was looking at how could we overcome that inherent design problem inside the electric motor. So we've got a dedicated facility at the university for testing electric motors and being able to create new programs that allow us to remove that or to test out how we might remove that torque ripple. And it turns out we were able to use something called resonance control, which is a little bit like noise cancelling headphones. So this ripple that I saw before is actually quite regular. It occurs over time. You can monitor it and you can see it very well. And so here we've got just an example of an experiment where after 3 seconds, so at the point of this black line, we switched on this resonance control approach. And we can see over about the next half a second, that torque ripple went from, or that speed ripple went from 20 to 30 RPM to about 24 to 26 RPM. And you sort of took a little bit of time to evolve, and that's the system picking up what this ripple looks like and then applying a compensation for that. And that's exactly very similar to what your noise cancelling headphones will do. If you first turn them on, it takes a little bit of time for them to detect the regular noises that are going on around you, and then it suppresses those regular noises very, very well. If in my case, your children then come along and ask you for a drink, it doesn't suppress those noises because they're not regular and repetitive noises. And so this is quite a young technology for us, but this is the kind of thing that is going to enable electric machines to be used much more widely, or potentially made at much lower cost, because we don't have to engineer the smoothness into the mechanical design. We can sort it out retrospectively. I'm now going to move on to talk about something about batteries. We're also interested in batteries. And I'm going to think batteries are really the core part of any electric vehicle going forward. And they're the core part because they're the most expensive bit, they're the heaviest bit, and they're the biggest bit. And so it really matters kind of how much these batteries weigh. And so we have we've done some analysis on a vehicle a bit like this, so a BMW i8, which is a hybrid vehicle with a battery pack inside it. And this is a sporty vehicle where weight really does matter. And just over on the right-hand side here, I've got a graph which On the bottom axis shows you what's called energy density. So energy really relates to how far, what is the range that you can achieve with this car. And this is sort of the range per kilogram of battery that you could achieve. And on the y-axis, I've got something called power density. So this is this isn't related to range. This is related to acceleration and how fun it is to drive this car. And again, that has a density to it. So it's how much power you can achieve per kilogram of battery. And there are a whole range of different batteries that you can buy, different chemistries, different designs. And it turns out you have to make a choice. You can either have batteries which are very energy dense, so you can have a lot of energy per kilogram, or you can have batteries which are very power dense, so you can have a lot of power per kilogram. But you can't have both. These points are all either up here, over here, or down at the bottom. And that's a challenge, because it means if you've got an application which needs a lot of energy but also a lot of power, then you have to compromise on the weight. And the weight is a really important part. You want to try and minimize that as much as you can. And so what we've been looking at is a concept of a split pack. So if you imagine a battery for an electric vehicle, is the idea of, well, let's split it in half, and let's have half of this battery pack using energy dense cells, and then part of this battery pack using power dense cells. So maybe a combination of this chemistry and this chemistry. And the question is, if we do that, can we make the overall battery lighter? And when you do this, you need a bit more control. You make it a little bit more complicated in terms of needing some more power electronics to manage those two batteries. But if we take all that into account, can we improve energy? Can we improve energy and power density overall? And it turns out we can. And but how much we can depends on how we're actually going to use the battery that we're designing. And so we like to define how we're going to use the battery using something called the power to energy ratio. And this really depends on the vehicle and the application. So as I said before, power is really linked to how fast do I want to drive and how much do I want to accelerate. And energy is all about range. And we can create this metric, which is just the ratio between the two, so power divided by energy. And if we've got something like a Renault Zoe, so say a family car for normal vehicle for driving around, this has a power to energy ratio of about 3. So it has a lot of energy because it's got a range of about 200 miles. And it doesn't need much power because it's not a particularly sporty vehicle. If we move to something like a Tesla Model S, so a very sporty, pure electric vehicle, then this has a power to energy ratio of about 6. It's a little bit higher. If we move around to the BMW i8, which is a hybrid, so here the battery pack isn't designed to drive the car for hundreds of miles. The battery pack's only designed to drive the car for about 20 miles. But this is a really, I guess, a sporty vehicle. And here we're talking about a power to energy ratio of about 35. And if we take it all the way over to the extreme, then talk about Formula One and the kinetic energy recovery systems, well, they hardly store any energy at all, but they have a huge power deployment, and they have a power to energy ratio of about 500. And if we start to consider those on this graphic at the bottom here, what this is showing is, again, energy density and power density for a range of these different power to energy ratios. And the blue line here represents the best we could achieve if we were just using one type of battery cell. And the green line that goes across here is the best that we can achieve if we use this split pack approach. So if we use two types of battery technologies. And so depending on our power to energy ratio, for the Renault Zoe, there isn't really much saving at all. You can see that down here with this line here, which represents the Renault Zoe, the green line and the blue line are together. When we get to something like a Tesla, there's maybe 20% benefit in battery weight by doing this. For the BMW, it's maybe closer to 25%. And we could imagine a whole range of other applications that might fit in between these two, where we could get up to sort of over 30% saving in battery weight by using that approach. That's batteries. So my last bit of research that I want to go in before I move on to sort of our future is it actually relates to the driver. And the driver for us is part of the propulsion system. In fact, it's perhaps maybe the most important part of the propulsion system. And so what we've done is quite a lot of work comparing what goes on in the laboratory versus when we drive around on the road. So here, this thing called New European Drive Cycle, NEDC, and this World Light Duty Transient Cycle. These are regulation cycles. These are the things on which are used to determine what the advertised fuel economy is of a particular vehicle. And this is just us driving around the country for 12 months, logging our data as we go to see Shell JCB, Jaguar Land Rover in Coventry, Ford in Essex. You can see all the sort of hotspots, Ashford's down in Exeter. And what's plotted on the bottom here is kind of the range over which the engine in this case is being excited. And what we can see is when we go out and drive on the real road, well, we're actually using the engine over a much broader operating space than in these legislative cycles. But these hotspots, so these red hotspots, they correspond to that lower left-hand corner that I was talking about earlier when I was talking about downsizing. We've also got things going on with emissions control systems, and anyone who's owned a diesel in the last 10, 15 years will have had one that was equipped with a particulate filter. And a particulate filter is something that collects all the soot that comes out of the engine, so it doesn't get thrown out of the tailpipe. But roughly every 500 kilometers, it has to burn off that soot. And when it burns off that soot, it creates a lot of another type of emission, which is called NOx. And this was my old commute to work from Gloucestershire. And what we noticed here was there was systematically the same location on my route back home from work, where we were seeing this regeneration of the particulate filter. Or in other words, if you own a house somewhere around here, you're potentially in quite in a NOx hotspot, despite the fact that you're somewhere in the middle of rural Gloucestershire. So they are complexities of an engine that the driver does have an influence over, but maybe doesn't know, or has far more other important things to think about when driving than to be able to also think about, is what I'm doing right for fuel economy, sustainability, and emissions. And so what we've tried to work on and continue to work on from a driver perspective is to think about how we can influence the driver in a way that does improve emissions, fuel consumption, but that is manageable in terms of the workload that a driver has to have when they are driving around. And so we've worked on this product called Lightfoot, which, very simply speaking, is an instantaneous driver feedback loop. So you get this small device that you put in your dashboard, and it has a series of lights going from green to red. And very simply, the more lights you have on, the more fuel you are consuming. And this product started life as a fleet manager's tool. So people, for example, who manage, say, in the post office, a fleet of drivers, their biggest bill is the fuel, and they would choose, they would sort of force their drivers to use this system to be able to encourage and enforce economical driving. But more recently, what Lightfoot are trying to do is turn this into a consumer product. So trying to turn it into something where members of the public will part with 150 pounds of their hard-earned cash in order to buy one of these tools, which will then subsequently help save them fuel. And it does work. It does. We did see up to 30% benefit in fuel consumption by using a Lightfoot system. The average was about 12%, and it does it by encouraging smoother driving. There's still work to do in terms of how that gets deployed as a consumer product, but that is more. That's starting to go outside the realms of engineering and into the realms of more of psychology and how it interacts. And this was a project, the most recent project that actually also involved the Institute of Advanced Motorists, IAM RoadSmart. We're a partner on this particular project. And looking forward, it's more complicated than just tailpipe emissions. So as we move to things like to electric vehicles, hybrid vehicles, we know how we can just get rid of the tailpipe emissions. And then we shift to other problems. And actually, brakes and tires are just as big a culprits in terms of particulate emissions, in terms of affecting air quality and human health. So how we fit that into the equation is really interesting. So I'm just going to spend now the last few minutes that I have talking about IAPS and our future. So I've shown you a little bit where we've come from at the University of Bath. I showed you the growth that we've had over the last 10 years, and I've shown you some of the insights into our research. And really, that research that's driven that growth has taken us to a point where a few years ago we were able to secure £70 million worth of investment to create what will be our new home, and this is it. This is a completely new research facility that's based out on the Bath and Bristol Science Park, so about 15 miles away from the university. This video was taken just a few weeks ago. We're still fitting out the insides of this building, but it's really getting close to being ready to go. And what this is it's a building that's really built around people. It's built around people in as much as we know we're an agent for collaboration. And so, yes, it's filled with lots of great test facilities, but it's also filled down the middle with this really large collaborative hub. And the idea being that people can come here from all areas of the automotive sector to work on, yes, their specific and secret projects, but they can step out of those rooms into this real unique space for collaboration. Yes, it'll also be underpinned by world-class facilities. We will have things that go beyond what I showed you before in terms of being able to test different parts of the system, a real focus on electrification and a real focus on modeling and how experiments and computer simulations can interact with each other. And this will really cement our place in as a kind of coordinator of efforts between vehicle manufacturers, SMEs, and tier one suppliers. But what we also recognise is that the industry is changing as well, and there are a lot of questions right now for the automotive industry. We are shifting towards electrification, but how do we know that we're taking the right approach? We've got it wrong in the past. We got it wrong with diesel engines of passenger cars. We've seen that in the last 5 years or so. Are we getting it wrong again? How can the sector and all its stakeholders make sure that we're making good or making the right choices? And the end user is one of those stakeholders, and their behavior really underpins whether we can succeed or not. And we've got to know, how do we regulate this business in a way that doesn't stifle innovation, so it avoids the big mistakes, but allows us to reach the best solutions. And really, for me, engineers alone don't have the answer to that. So we're going to go beyond electrical and mechanical engineering going forward. And that just brings me on to talking about our doctoral training centre. This for me is really the future. These people here are the young researchers who've been with us for less than 18 months, who come from all different areas. Yes, there's some mechanical and electrical engineering students, but there's also biologists, chemists, psychologists, social science, mathematicians, computer scientists, data scientists, civil engineers, and business students. And they're all coming together. They're all working together on the big challenges around automotive propulsion and how we can move around sustainably going into the future. And that's a really big task for them, because transport uses a lot of energy and it makes a lot of CO2. It's about a quarter of our emissions is linked to road transport. And also we've had many years of social trends which have really led to the dominance of the personal car. So these are just some things I took off the BBC website from a few years ago, which show kind of the growth in passenger miles of cars, vans, and taxis versus all other forms of transport. The number of households that don't own a car has dropped quite significantly in the last 50 years. And the cost of owning a car has actually stayed relatively low compared to other forms of transport, and that may not be able to stay the same way in the near future. So but that's where we are, and that's the trends of history. And it's really complicated because we're making this shift from petrol and diesel to electricity. And it's very easy with images like this to think that one is just a substitute for the other. That, okay, I used to put the pump in the car, now I put the socket in the car. But actually what's happening is, in replacing in the car electricity for petrol and diesel with electricity, is we're actually changing an energy source. So petrol and diesel are energy sources by an energy vector. So, and in that sense, what I mean is you can't just go and mine electricity out of the ground. You have to create electricity using fossil fuels or renewables. But electricity itself is not something that we can just go and collect somewhere. Electricity is a means of moving energy from one place to another. Whereas our conventional petrol and diesel, it's mined out of the ground. It is an energy source. But we're not really necessarily making that distinction very clear. And if we start thinking about hydrogen, it might be easy to think of hydrogen as an energy source as well, but hydrogen is actually an energy vector as well. You can't mine hydrogen out of the ground. Hydrogen is a way of moving energy around. It just happens to be a bit more energy dense than electricity. And my final point, and I think I'm right up against the hour mark. I just wanted to bring out some examples of what we're doing right now. And this is just two headline brochures I took off the Renault website. Why Renault? Well, I own a Renault Zoe and I absolutely love it. So I'm a Renault fan at the moment. So at the top here we've got the Renault Zoe. And this is driving range of 245 miles. That's what this car is being sold on. How many miles you can drive. This Captur, which is a combustion engine with a mild hybrid system. The headline here is all about 40% reduction in fuel economy. And so what happens is the electric car at the top here is being sold on the basis of range. Range is basically equal to how big is the tank. It's got nothing to do with efficiency of the vehicle. It's just how big is the battery. If you put a bigger battery in, the car will go further. Whereas the hybrid down here is being sold on the basis of efficiency. So this hybrid down here is actually being is more aligned with sustainability, which is all about being economical with energy, than say the electric vehicle, which is being sold on range. And I don't have the answer to this, but I observe this and I think, are we going about this in the right way? Should we have just an infinite pursuit of more and more range from our electric vehicles? So just in closing, some closing remarks then. So for me, it's a really, really exciting time to be working in the automotive sector. There's really diverse technologies, and then sort of over the last couple of years, really diverse people. It's been fascinating for me to work with psychologists, with business students, and so on, people who I barely understand, and they barely understand me. But we still really want to make this work. The challenge for sustainable mobility is really big at this point in time. It's huge. And there's so many stakeholders involved that we have to work together. We need that diversity. I think this picture from Nottingham is really, really interesting to see just all those different modes of transport and how they interact with each other. And for me, there's a question of how do we engage with the end user with regards to this complexity. So, in other words, how could we perhaps take something like Lightfoot, which is just seeking to improve fuel consumption inside one car, into a platform that maybe really helps individuals to make sustainable mobility choices? And it probably won't just be a gadget. It'll probably be a combination of gadgets, tools, the technology, and education of people. And that's really a point that I wanted to leave on, because I think that really aligns to some of the potential missions of the IAM going forward. And on that note, I will say thank you very much for listening, and I will open the floor for any questions, assuming you're still there.
Hi, Richard.
Just going to stop the recording just a minute.